You happen to know how to turn the slides down? Like, oh, perfect. Which,
Yeah, so we can also.
there, beautiful.
Yeah, maybe a little bit of like for the speaker would be good, so we can.
This is the one we usually use, and did you wanna?
No, thanks, let us
Okay.
do the. Here, okay.
It's there, so there's also a
Oh,
laser pointer.
Oh. Thank you.
So I think we're good.
We're good to go?
Yeah.
All right, let's get started so we can use the full hour. Welcome everyone to the AstroAI lunch talk. We're very delighted to have two speakers today, David Fouhey and Eirini Angeloudi. David will go first. David is a assistant professor at NYU. His PhD was from Carnegie Mellon in robotics, actually, and he works on a number of problems related to computer vision. And he is an old friend of some of the people in the audience here. So he's going to tell us about adventures in using computer vision for solar physics. Take it on. Thank you.
Thanks so much. So I'm going to be talking about work, and this is work that's been going over a number of years in collaboration with 3 of my students, as well as a large number of collaborators from lots of different institutes. So, see, is this working? All right, cool. So here's the sun. And so one of the fun things about the sun is it's all the data is actually very fun to look at. And this is actually in large part why I started working on this problem. Someone called me up and said, hey, we have this interesting problem. And they started showing me the data. And I thought, this is really, really cool. Because if you look at this is actually 3D structure, and this is being caused by a magnetic field in the corona. And I'm actually originally a 3D computer vision person. I've sort of wandered into a number of different fields, ranging from understanding how humans interact with objects to now working on solar physics. And underneath, this is sort of an extreme UV observation of the sun from an instrument called AIA on SDO. And underneath this and sort of is a magnetic field, which we can measure the best at the photosphere. And so here is the radial component of the field. And so the color map going from orange to purple. And so the magnetic field changes quite a bit slower than the corona, which is being shown at the top. But the sort of magnetic field is where we can, the photosphere, which is in the bottom, is where we can observe this magnetic field the best. And so I've been interested in how do we get data that enables people in astronomy, such as people like yourselves, to do better sort of science. And I've been working on this for a number of years, and I'm really happy to now to show you some of the stuff we've been producing. So one of the things I'm very interested in is getting the 3D structure of the sort of magnetic field. And so what we can, for those of you who don't know much about getting magnetograms of the sun, the photosphere, which is sort of what you can see on the bottom right and the left ones, is where we can best observe the magnetic field. And thanks to a number of instruments, we can actually get the three components of the magnetic field. So we can get the radial component, which is facing outwards from the sun. And then there are 2 other components, which are basically, you can think about them as longitude, latitude. And this is a quantity which is of tremendous interest to solar physics researchers. And so one of the reasons why I got interested in the magnetic field was I realized that this was sort of a cornerstone data product that tons of people use. So for example, here's a magnetic field map. This is a magnetogram of the radial field covering the entire sun. So this is the sort of 4 pi steradians of the full sun. So if you've ever looked at a video game, this is basically like a texture map. And this is the type of data that people use to drive simulations, for example. The other thing people use with magnetograms, they use them to do things like flare forecasting. So you have information about how the vector magnetic field changes as a function of time, and you can use this to predict, for example, is there going to be a flare in the future? And the really cool thing about this is there is tons and tons and tons and tons of data. So I do computer vision, which is in largely learning-based computer vision. And for this, the more data you have, typically the better things are. And one of the things that I became interested in is producing better magnetograms for people to do better science with. And so some of the goals that you might have for producing magnetograms like this is you want it to be accurate. This is the most important thing. You want to cover the full sun as much as possible. You only realistically see sort of 2 pi of the sun, not the 4 pi. You want to have things like, for example, have low systematic errors. And this is something we typically don't talk about in normal computer vision. So at CVPR, no one is talking about your systematics. But as it turns out, astronomers are very, very concerned about this. So this is a fun challenge. And one of the other things that was kind of fun is that we want to be able to produce these magnetograms really, really fast. So for example, the instrument that I primarily work with, Solar Dynamics Observatory, it's been operating for the mission's been operating for 14 years. And so there's 14 years of data, which is captured every 12 minutes. So there's enormous volume. And so stuff that's slow might be very interesting, but I want to be able to produce lots and lots and lots of data. So we need it to be fast. And so before I talk about the machine learning we've been doing, I want to give you a brief overview of how people actually get magnetograms in practice of the sun. So you can't actually build an instrument that senses the magnetic field. So what people do is they produce other observables. So here are the Stokes vectors. So this is polarized light. So intensity, then two linear polarization states, and then circular polarization. And this is of the sun, and you get it at different pass bands. And this full sun, there's tons of stuff going on, so we can zoom into an active region. And so these different pass bands sort of capture information about the sun's state. And so you have an instrument that will capture these. So these are 6 pass bands from HMI, which is sort of a key instrument for capturing the magnetic field. And what happens is that you get the vector magnetogram, so the vector direction of the magnetic field, by disentangling the Zeeman effect from a bunch of other things. And so what happens is that if you have the magnetic field, so white here is no magnetic field, orange is facing inwards towards the sun, and purple is facing outwards. If I have light that's being emitted from the photosphere, you have an absorption line. So you pick your absorption lines very carefully based on their properties. And with no magnetic field, you have basically, okay, there's an absorption line, there's the intensity dips. And in the presence of a strong magnetic field, so here inside this sunspot, you get Zeeman splitting, and so the single absorption line turns into 3. And of course, there are lots of other effects that are happening. So for example, there's redshift, so the sun is rotating both towards and away from you at the same time. The instrument itself is going back and forth. And so redshift, for example, will shift everything over. And the details are incredibly complex, but what happens is you traditionally solve a classic optimization problem where you try to reconstruct the light you see according to a physics model. And it's really, really complicated, and these instruments are amazingly well designed. So you have limited spectrum resolution. You need the polarization to get the angles. So you actually to get the full vector field. And then, in fact, everything is actually up to a 180-degree ambiguity that you actually can't resolve without injecting additional information. And so, given the limited amount of time, I'm not going to talk about sort of how you really do, how you actually get these magnetograms, because it's, you could talk about entire days worth of talks on how you get this. But the good news is that there are lots of systems that produce this. And so one of them is you have essentially a constellation of systems. So HMI onboard SDO, it has an instrument and a pipeline. So it's, for example, it's full disk, so it captures the full sun. It's a coherent image in the sense that it's actually an imager. It captures a single snapshot of the full sun all at once. And it has really fast acquisition time. So you have 14 years of data at every 12 minutes, you have a magnetogram. In fact, you have data products that are actually faster than that as well. So you have immense amounts of data. The catch is that there are only 6 pass bands of spectral sampling. So actually, the magnetogram is amazing, but the quality is only okay. I have to be very careful about what I say, because this is an instrument which is designed for specific things. The instrument itself is great, but for certain types of studies, it's not the type of instrument you want to use, because it only gets 6 pass bands. And so its ability to recover information about the magnetic field is actually a little bit limited. There are other instruments as well. So there's Hinode, so is a mission, which is JAXA and NASA. And on board is SOT-SP, which is another spectral polarimeter. And it captures images like this. And in fact, if I were to display it the way it actually captures it, we'd actually have to wait for the entire talk in order to see the sort of full picture. So it takes about 30 minutes to an hour to capture a single image, basically. And it produces other, it has its own pipeline that produces its own magnetograms. And it has much, much denser spectra. So it is, let me just delete this, let's enter this again. Okay, so it captures 112 wavelengths in this 4 polarization states, and it has much better and more accurate magnetograms. The catch is it has a small field of view, it has a slow acquisition time, and there's very sparse coverage of activity. And in fact, I'll show you some of this. And so, well, we have 2 instruments, and we have them co-observing. So what can we do with this? And so they have complementary missions, they have complementary strengths, complementary weaknesses, and there's over a decade of co-observation. So I'm a computer vision person, and when I see something like this, I say, hey, wait a second, why don't we use machine learning to get the best of both worlds? And actually, way back when I started my PhD, this is something I did where you had an instrument basically an ordinary RGB sensor and another instrument, which was like a depth sensor. And you use the two in together to produce something that produces depth without needing, for example, extra special sensors. And so we've been building a system, and due to the length of time, I'm just going to give you a flavor of the types of machine learning techniques I'm using. We can talk about it later if you're interested, but I just want to give you a few things we found to be extremely helpful. So the overall method that we do is we basically, at every single pixel, we try to discretely categorize the what the value of the magnetic field could be, basically. And so, for example, it might range from negative 4,000 Gauss to 4,000 Gauss, for example. And this is a trick which has been used a lot in computer vision in things like depth estimation. So you actually, rather than predicting a continuous number, you actually predict a discrete quantity. And there are a number of reasons why this is useful. And we use something like a basic UNet. And so this is a very bog standard computer vision technique for predicting for like a deep learning architecture. And the reason why I'm trying to use very standard things is often what happens is when computer vision people jump into a new area, sometimes they'll bring in very fancy techniques. And what happens is you really first need to see whether the very basic stuff works well. And then if it doesn't work well, then you want to add the fancy stuff. But my goal in my research is to have something be very simple, easy to implement, and be effective. And only once we realize there's a limitation, do we add more complicated stuff. So there are lots and lots of other architectures, other things we can try. But this is basically, we try to predict a discrete classification for every single pixel. And there are a couple of tricks you can use so you don't end up with sort of artifacts coming out of this. And so, for example, here we might predict that it's more likely that it's negative 2.5 thousand Gauss, and it's much less likely that it's, for example, 4,000 Gauss. And the cool thing about this approach compared to other things is you can get uncertainty quantification in one pass of the network. So if you can run the network once you pass the image through, you can get essentially an understanding of how certain the network is, because actually propagating uncertainty is very important. And it's also resistant to outliers during training. So if you have weird values, which is often common in pipelines, where basically you have more data than a human can look at, this type of approach is pretty resistant to outliers, as opposed to regression-based approaches, which kind of bake those into the predictions and can end up with sort of weird biases as an output. And we originally developed this, we first started to try to just accelerate one missions pipeline entirely. So it was just, we didn't worry about any other missions. We just first tried to get this to work really well on one missions pipeline. We could get results that were, say, 100 times faster than the existing optimization-based systems. So what we then did is we said, well, why don't we just take two missions and put them together? So we can take one instrument and use it to supervise the answers for another instrument. So SDO-HMI captures this lower quality in terms of spectral resolution data. And we have this Hinode SOT-SP, which captures higher quality data. So we'll use the answers from the SOT-SP instrument to supervise something, and the inputs come from the HMI instrument. And so this is, again, a technique which has seen a lot of success in lots of computer vision. And we're trying to bring this to solar physics. And we call it, the people we work with love sort of acronyms. So they said, you have to have an acronym. So we're fine. So synthetic inversion approximation, Cynthia. And so this was we built a first version. Now, one thing that we ran into, this will probably make Bill very happy when he sees the solution to this, is it turns out that the SOT-SP instrument's pointing is off by about sort of 30 arc seconds, or about 60 pixels. And it wasn't until I actually started playing with the telescope myself that I realized how difficult it is to actually know where you're pointing. And so the instrument itself, SOT-SP, points at a very small region, so it's very hard to figure out exactly where it's pointing. And so it's inaccurate. It kind of varies as a function of season. And so we need to fix it. And so we solved this via a sort of careful application of a standard computer vision technique, which was something called sift and ransack. I teach this in my computer vision course. Their careful application here is because the instrument itself is a scanning slit spectrograph, so it doesn't actually take a coherent image. And there are lots of other details that you have to get exactly right, otherwise your answers are wrong. But the basic technique is something that is sort of like a thing that was used to do things like build Street View, for example, and build large-scale reconstructions in computer vision. But we're able to co-align the instruments very nicely. So you can co-align them against other missions. So SDO has been up since 2010, and before that there was SOHO, which also has an instrument you can co-align with. I'm going to show you on the y-axis is how much the instrument is off by. On the x-axis is time since the launch in terms of years. And I'm curious if anyone can spot what might be the pattern in terms of, and I'm coloring them according to the time of year. So going from red in January to cyan in the middle of the year to red at the end. Does anyone spot when it tends to be off, and does anyone have any ideas about what could be the cause? So it certainly gets worse over time.
Well, perihelion is January 4th. Does that have anything to do with the ellipticity large?
It has to do with an orbit, but it's not with the not Earth's orbit. But it is, that's the right general direction.
Where's the thing? Is it L1 or?
No, it's sort of I don't know the precise term for the orbit, but it basically goes around and then once a day goes over Svalbard to send the data down. So it's in a
Oh, it's in North orbit.
yeah, it's in Earth orbit. Yeah.
Oh.
Other guesses? Well, it has to do with basically the orbit, and what happens is during there's essentially a part of the year the instrument is in shadow a lot more, and so it does tie to the orbit, but it's not the distance from the sun, and so it's in shadow a lot more. And what happens is you can actually start tracing this back, and you start reading through all the headers, and eventually you figure out that it's basically the temperature, and the instrument itself gets cold, and something bends, and it's been bending periodically on and off, freezing, unfreezing, freezing, unfreezing over the course of like a decade. And so this actually ends up causing the issue, which was actually kind of fun to diagnose this. Okay, so, but once you get all this data, you can, for example, produce co-aligned data. And so this includes things like the poles. We have about 13,000 scans from Hinode, and now it's up to about 16,000. And we also were able to fix like a 1% error in basically the angular resolution, which was kind of fun. Now we can train a system that basically predicts what would SOT-SP see if it were looking at this pixel in HMI. And we have a new version called Super Cynthia. I'll let you figure out the etymology for that one. So it has more data, it can produce components that are needed by physicists. So it resolves a key step called disambiguation. And there are a couple of tricks that are in the paper. I'll just show you one trick, which is kind of neat and kind of nice to see. But there are lots and lots of tricks. And this was a result of sitting with our collaborators and asking, what do you really want? One of the tricks was that in a lot of the data we're dealing with, some of the quantities are just fundamentally unresolvable and they're poorly constrained. So for example, the azimuth, which is basically the angle of the vector in the plane of the sky, actually in many parts of the sun, because there isn't enough polarization information, isn't resolvable. So here the color map goes from 0 to all the way around. And depending on the transverse field strength, basically how much of the field is pointing through sort of the plane of the sky, at some parts you know what it is precisely, and some parts you really don't know what it is because the vector isn't long enough. And what happens is that when you train a regression model, the regression model averages over all the possibilities, and it will produce something where it's on average to be like 90 degrees, for example. And the regression model, because it can't predict what it is, and so it just predicts the average. And so this is a very bad result, because what happens is that most of the disk of the solar disk is pointed in one direction, which basically, if you plug this into a model, is completely bogus. If I take the most likely output from our models, which sort of predicted distribution, you end up getting sort of structure. And I actually chatted with our collaborators, and this structure is completely bogus. This doesn't make any physical sense. And what happens is there's typically some amount of bias in your data, and the network just captures this. This is the same phenomenon that happens in machine learning models on the internet, where, for example, it will replicate societal biases in terms of like how people are depicted in images on the internet. And you have one trick, which actually comes from the auto processing community, which is called dithering. And so what happens is you can take the log probabilities. So in the uncertain parts where you don't know what the direction is, the distribution is basically flat, but something happens to be slightly more likely. In the certain parts, there's a very clear peak. And what we can do is we can add a bunch of noise. So this is dithering noise. We just add a bunch of noise. You have to carefully constrain it. And then you add it back. And what happens is it bumps the distribution one way or another in a sort of random direction. The confident stuff, it doesn't change. The non-confident stuff, it essentially becomes noise. And so this lets you actually get this output where the part which should be evenly distributed is evenly distributed, but without actually mucking with the parts where you actually know what the answer is. And so let me just show you a video. We're going to start with the most likely answer and add more noise, and then add too much noise. So here, pixels start changing. And then this is basically the right amount of noise where all the unconfident stuff is sort of roughly uniform. And they can add more and more and more and more noise, and then essentially all the structure disappears. And this can be done in a single pass, so you don't have to run the thing multiple times to get this answer. So it's a neat trick which enables you to do this. You can run this sort of at test time. And it gives you, yeah.
You have a principal way to know when to stop?
We actually picked, it was the first value we picked, which was, you had a roughly uniform. roughly equally weighted. So the essentially adding one, sort of a standard deviation of one in terms of the logits. The noise itself actually it can't be Gaussian. We actually use something which cuts off very early. So it's like a triangular noise. But there's stuff where really, if you have it way too high, it's very obvious, and way too low, it's very obvious. But you could probably also tune it pretty easily. Let me just show you, let me just skip over this. All right, I'm going to show you some results of the system in action. Before I say this, I'm going to show you primarily edge cases where the HMI pipeline is known to not work. So I'm not saying the HMI pipeline is bad. Our method also has its own issues, but I'm picking stuff which is these extreme edge cases. So here we're going to look at BR. This is right before the largest flare of 2016. And so we're going to zoom in, active region. And on the left is us, and on the right is the normal pipeline. So if you look at here, if I go from frame to frame, things flip back and forth. And this is completely unphysical. And if you actually plug in this data, the system has to explain why all of a sudden the magnetic field flipped from facing outwards to facing inwards, for example. We're going to actually zoom in a bit more. This is, by the way, during flux emergence, which violates all the assumptions that the pipeline uses. But here we're going to look on the left is our system using deep learning, and the right is the classic optimization thing, which is done, both these are done per frame independently. So we don't have any smoothing on. But what happens is our system ends up being much more smooth. So on the right is the pipeline, and you can see stuff flip-flops back and forth pretty frequently, because there are two solutions and it can't pick which one. On the left is our system, and it's able to produce much smoother results. And what happens is it has to work, our system has to work for all the pixels in the training data. So it has to sort of decide how does it resolve the ambiguity in the training data. And so at test time, the results look pretty reasonable. We also get rid of certain like small artifacts or like checkerboarding artifacts that are a result of the data processing. Let's see. So here's more of the system in action. And then as the stuff gets towards the center of the disk, everything looks pretty stable. But as you get towards the limb, both systems end up being a little bit unstable. And so this is actually one of the things that I discovered in solar physics. They have all this beautiful data of the sun. And then the reality is that only sort of a moderately sized part of the center of the disk is actually really usable. And so some of the stuff that deep learning can do is it can bring stuff further and further out to more extreme viewing angles. And so as you're on the limb of the disk, there's tons and tons of flickering in the existing pipeline data. If I paused any of these frames and stopped, any of them would look okay. But what happens is it flip-flops back and forth between two plausible solutions. You might be curious, why don't you just use the higher quality instrument? And so here is what the higher quality instrument is doing. So right now, this is in the lead up to the largest flare of 2016. It's looking at this region of plage, which is very scientifically interesting. And the entire point is it's not an operational mission. It's not supposed to be doing flare forecasting. So it's doing its science thing, looking at stuff. And there's this active region that's evolving. And it's only much further on that it starts actually looking at the active region. And this is because the mission that we're using the answers from is, again, it's a science mission. And so you have to upload the data, you have to request for the instrument to point at the quantity of interest. Okay, I'm gonna briefly just mention two things that we're doing. One of the things is that right now we're trying to use the data, we're trying to use the existing system that we've developed to use for science. And this is something which I'm very excited about because we're trying to enable people to do new cool science. So one of the things is you can have this map of the full sun. And so this is accumulated over many observations. And what you can do is you can use this as a boundary condition for a MHD model. And so we're now working with MHD modelers to try to use our existing data to try to produce better models. And at this point, I'm not hoping to do better than the sort of existing data. My entire hope is that as a machine learning person, my expectation is you take machine learning generated data and you put it into a new system. Often the answer is that the system catches on fire and doesn't produce any good results. So I'm happy with, can we produce reasonable data? Because this is actually a good validation of, did we produce reasonable results? And so what you do is you can run an MHD model, and then you measure things like the velocity of the solar wind and the field strength at another instrument. So this is solar A. And the observations, here is the existing pipeline, which there's an entire art to figuring out whether your solar wind predictions were correct or not. I don't pretend to know what it is. So they'll look at it and they'll say, this is a good result, this is a bad result. This is one of the joys of collaboration. They'll tell me whether it's good or not. I can't, you can see some similarities. And then our existing system produces results that are on par with the sort of the standard pipeline, which is kind of fun. which is I think is, it's a good result given that it's machine learning generated data. We're also doing things like extrapolating into the corona, so we can use our systems. Currently, I have two collaborations where we're trying to use this data to produce better estimates of what's going on in the coronal magnetic field. And finally, I'll just show you to close up. I'll show you where some of this stuff can go. So having a method that produces data like this opens up new capabilities and sort of things you can do with it. So once you have a validated method that produces reasonable results, now you can do all sorts of cool stuff. So one of the things that happens is when people measure the sun's magnetic field, you want to measure this vector B. And so you're looking at this. And so this is, for example, highly inclined away from the viewer. And the way that you get the line of sight data is from Stokes I and V. And you get the perpendicular data is from Stokes Q and U. Now, as it happens, if you know about observations, Q and U is very hard to measure. It has a worse, like an order of magnitude worse signal to noise than I and V. And so, if you get this, you can sort of measure, if you want to get the radial component, you can calculate it from the line of sight and the perpendicular component. And so most of the time, for a lot of instruments, you don't actually get Q and U, so you actually can't measure the perpendicular component. So what people do is they use the line of sight component and they fix it. And they fix it, what happens is they sort of account for, they assume that it's radial and they re-normalize the vector. And this often produces bad results. And so I'll show what happens. I'll show here's actually the data. Remember the solar storm that caused the aurora in May 2024? So here's the vector data that is for the active region that caused it. So I'm just going to show you the data here. There's complex structure emerging, and this is right about when the flare, like a large flare, like a X5.8 flare, is going to start. And what happens is the data that people often are using is the stuff on the left, and what we actually want is the stuff on the right. And so I'll actually show you how to spot the differences. For large parts of it, so there's a sunspot on the left, which is in the correct data, it's all orange, so all facing one direction. In the data that a lot of people use, which is line of sight data, it's actually completely wrong. So this is off. And there are lots of other things which are wrong. And so we're able to produce better data actually by using our existing technique to actually correct these line of sight magnetograms. So this is something we're currently working on. And with that, I'll just show you one last thing, which is why this is important, which is you can go and look at lots and lots of data from lots of different observatories, including stuff that is quite old. So from previous solar cycles. So back in 2003, back when Finding Nemo came out and iPods looked like that, there's data which goes back many solar cycles, and the only data we have is line of sight. And so the top is a sunspot, which is wrong if you've seen a lot of sunspots in your life. And the bottom is a result that comes from our system, which is able to correct this and produce much better data. So with that, I'm basically out of time. So I want to conclude with basically, I'm on a quest to make data that people want to use for science. And so I've been happy to work with a lot of people. It's a quest and it will take a while. One of the things is that computer vision can really help, and including, by the way, classic computer vision. You don't need to go for, there's lots of cool things you can do with the stuff that predated deep learning, and it can often work really, really well. The best results are using domain expertise. I couldn't have done this without my collaborators. And the validation is really hard and important and still going on. So with that, there are two talks, so I want to turn over to the next speaker as well and take any questions.
Oh, sorry, you have to rush a little bit. I encourage everyone to stay after the hour if they want to talk to either of the two speakers. We have time for maybe one or two quick questions. Yep, Bill.
This is really fun stuff. I don't know if it's a sociology question or a science question, but you mentioned that with the work that you input, the machine learning output, you inputted to the MHD simulations of the sun, you're just happy if their simulations didn't blow up, but using your ML generated data. But how can they possibly find it useful if that's the criteria for success? How do you get science out of that?
Yeah. So okay. So part of this is actually an interesting sociology question too. So one of the big challenges is that the MHD models the current ones don't actually use the resolution that we're able to produce. So we can produce stuff which is at much higher resolution, and the MHD models, the very first thing that they do is they downbin to 1 degree by 1 degree data. So what I think often happens with the ML for science stuff is you often have a product, and then the existing techniques are all designed for the previous product. And so they downbin to 1 degree by 1 degree because there are issues. So if you all flip-flop back and forth, that stuff gets covered up if you downbin to 1 degree by 1 degree. And so one of the things we're hoping to do right now is we're on this, we're saying, okay, here's the data. We'll produce any data you want, any date and time, we'll produce the data for you. And can you use this to do something new and interesting? And I think that takes a little bit of time because people just don't have access to the sort of like the higher quality data. So at the very beginning, you just want to make sure it works, because this is, once it works, people say, oh, I get the same results with my old system. Can I now do something totally new? And that's the sort of much longer term thing. And as you know, it takes years to convince people, essentially.
All right. What was that?
If there's any other question.
Quick one.
So we have, there's a very similar but opposite problem for trying to get MHD maps for stars, for running MHD simulations of the winds for stars. Then you have the opposite problem. You have very low resolution magnetograms, and I wonder, and very little data. And I wonder if something that we learned from the sun could be applicable to get higher resolution of those maps, at least for sun-like stars.
Totally. I think this would be super interesting because with the sun, you have all this great data and you have this high resolution stuff. So it might be able to constrain what are the plausible possibilities. I mean, the big challenge, I think, for a lot of this is that the simulations themselves are still under development, in the sense that in computer vision, the simulators we use is graphics, essentially. And graphics is a pretty solved problem because in ordinary day life, you don't have the unusual radiative transfer problems that you have in stars. But definitely, I think it'd be very interesting to combine the two, because also the one last thing is that in astronomy, you have lots and lots and lots and lots of instances, whereas the sun, you have this one specific star, and you don't get to see it at different points in its life. You are stuck with the data you have, which is a big limiting factor.
All right, we will move on, and I am happy to introduce the second speaker today, Eirini Angeloudi. She's visiting us from the Instituto de Astrofísica de Canarias in Tenerife. So she's actually currently visiting Laurent's Carole Levasseur's group at Montreal, and she's going to tell us about simulation-based inference for inferring the emerging history of nearby galaxies. Take care. Thank you.
Thank you. And thank you for giving the chance to present here some of my data. What? It's not working? Okay.
Yeah,
Sure.
put it
Closer? Yeah.
Yes.
Okay. Can you hear me now? Yeah, okay, perfect.
I can hear you.
Yeah. So, okay.
Maybe you put it on the other side.
Yeah, maybe it's better. Sorry. Better?
I think.
Okay, perfect. So, yeah, as you can imagine from the title of my talk, I'm quite interested in galaxy mergers. So galaxy mergers are these cosmic events where two or more galaxies come closer to each other and due to gravitation eventually collapse into each other and merge into a larger structure. And galaxy mergers actually come in many different flavors, as you can see from these beautiful images here. We can have major merger events that are between galaxies of similar stellar mass, or we can also have minor merger events. For example, when you have a central galaxy absorbing like a smaller satellite. And as you can see from these beautiful images, we can also capture mergers at different stages of merging. So you can have pre-merger events where the merging hasn't concluded yet. And you can also capture the merging event after it has already happened, where you can still see some traces of these nice, beautiful tidal tails, showing that something has happened here. So why do we want to study them? Well, we know that actually mergers have quite a variety of effects on galaxy evolution. So for example, they can trigger very intense spurts of star formation, especially when having to deal with very gas-rich mergers. They can even cause structural transformations and shift galaxies. Like, for example, you can have two spirals merging and then ending up in an elliptical galaxy. They can fuel the central black hole and other many interesting things. But unfortunately, detecting them, it's not so straightforward as it sounds. So as you can see from this image on the right, when you go to higher and higher redshift, it's not always very easy to tell a merger apart from, let's say, two non-interacting companions. So traditionally, how this was done was trying to identify close pairs in close pairs, both spatially and also spectroscopically. Or you could also try to identify some aftermath of the merging event, as I said before, like some morphological disturbances, like asymmetries or tidal tails. But of course, like in all fields of astrophysics, ML found its way also in this field, and actually quite successfully. You can use machine learning to classify events as mergers or non-merger events, and you typically can do this training on visual classifications with the data samples like Galaxy Zoo, or you can train on mock data from simulations and then solve this classification problem. But what I'm more interested in is a kind of a more archaeological approach. So not just classifying an event as a merger or not, but looking at how a galaxy looks today, and then trying to understand from that how its merging history has looked like in the past. So how many major or minor merger events it has undergone, when in time did those happen, more or less, and also what was the effect of these merging events in the stellar mass of the galaxy. So this kind of approach, as you can imagine, it is quite more challenging, and it has been done for this reason for very limited samples of galaxies. So for our own Milky Way, since we're inside it and we have all this wealth of data, especially now with the Gaia survey, you can actually resolve differences in populations, in different star populations, and more or less connect them with different merging events. So this is a whole field of study in the Milky Way studies that is called galactic archaeology. And I think now more or less there is a consensus, like I'm showing this nice plot here on the left, about how this merging history for the Milky Way looks like. But to do this for external galaxies outside our own, of course, this is a way more complex problem. You need very high quality data with resolved stellar accumulation properties. And so this has not been done very extensively. And also there is another way you can do this. You can do orbital decomposition methods, but these take a lot of time to run, maybe 2 days for one galaxy. So this is not also something that you can do for a statistically significant sample. So if you want to do this with high statistics, what you have to do is to rely on simulation-based inference, which is what I'm going to talk about today. So this was supposed to be a video on the right. So now let's just all imagine that you can see those two galaxies actually coming closer and merging together. So this is, of course, is coming from a simulation. This is not something we can observe in the sky. So the nice thing, when I talk about simulation-based inference, in my case, I'm going to use cosmological simulations, which are these big boxes where they simulate galaxies, and you can actually trace them all the way, trace their merging history back in time. So you have this kind of ground truth available. And then you can even track the origin of each star in a galaxy. So you can know which stars were born in situ in the galaxy from gas already present in the galaxy, or which stars have been accreted from merger events from other galaxies. And this is what we call ex situ stars. So what we're focusing on our kind of archaeological approach is trying to see if we can use observable features of how galaxies look today. In our case, this will be IFU maps from nearby galaxies. And we want to see if we can use this kind of features to predict this unobservable quantity related to the merging history of galaxies, which is the fraction of stellar mass originating from mergers, which is what we call ex situ stellar mass fraction of the galaxy. So to do this, when you're using simulation-based inference and you want to apply this on real data, you always have to make sure that you're taking care of all the biases that you might encounter as you traverse all the way from the simulation space all the way to the real galaxy space. So the most important thing here is making sure that you're not very tied to a particular cosmological simulation. We know cosmological simulations work quite well in reproducing realistic galaxies, but we also know that currently they are not perfect. So they have these inherent biases because they cannot model everything up to like all the small scale structures. So they are using some subgrid physics that they might induce some bias in our simulation-based inference model, and maybe we carry this bias all the way with us when we apply this on real galaxies. So we have to make sure that we remove this kind of bias and marginalize at least two cosmological simulations for our results. So starting in the simulation space, at the beginning of my PhD, when I started first with this project, I first wanted to make sure that this was actually something we could get, that you could actually train a machine learning model on this kind of observables and then predict this unobservable feature. This is the fraction of ex situ stellar mass. And back then we found that yes, in a single simulation scenario, actually you could get this quite accurately. So here to demonstrate that, I'm just plotting how well we can reconstruct the ex situ stellar mass fraction versus the stellar mass relation that we can get from the ground truth of the simulations. And here again, I'm only showing a single simulation scenario. So training one cosmological simulation and then testing in the same simulations. As you can see, we're getting for both simulations quite nice results. But the problem arises when you're doing this cross-domain test. So as you can see here, it's quite obvious that we have this domain drift. So there's a particular recipe in the simulations that does not let you do this cross-test. And this is something concerning. So this is certainly not a model that you can go and apply in real data, because you already know that this is not marginalizing well across different physics. So what you can do is go and explore in your input space and try to find some robust inputs that not only give you high accuracy in your predictions, but also abide well to this cross test. So this means that you manage to find features that can predict this ex situ stellar mass fraction value independently of the underground cosmological model that you have. Alternatively, if you don't want to do this exploratory search, you can also use domain adaptation, which is a technique that has been widely used in astrophysics, because this gives you the chance to use a source domain that you already know quite well, and then transfer this knowledge to a target domain where usually it's unlabeled. So in our case, we tried to see if this could work in our data set with adversarial domain adaptation. So in principle, how this works is that you have like your classification problem, let's say, and you also add a domain classifier ahead that tries to classify an image from which the origin of the domain that it's coming from. So also here you have like a gradient reversal layer. So essentially you're trying to extract features that the domain classifier is not able to tell apart from which domain it came from. So in our case, what we tried was try to see if we use as the source domain one simulation and then as the target domain the other simulation, but without any labels, if this was enough to remove this domain drift. And essentially, we found out that yes, it was. Even now that the model never saw any labels from the second simulation, it was able to remove this domain drift. So that was good to find out. So now that more or less we had a way to go around this domain problem that we had before, now we could move more confidently in the next step. So this is training in synthetic galaxies coming from simulations, but also matching the realism of the survey that we want to apply this. So our final goal was to apply these simulation-based models on manga galaxies. And fortunately for us, a data set mocked exactly like manga coming from a simulation already existed. It was called Mangia, and it was also statistically significant. So we could use this kind of data set to train our machine learning model. Unfortunately, life is never so easy. So we found out that this Mangia data set, of course, it wasn't built with the current application in mind. So it was quite unbalanced in terms of what we wanted to predict. So of course, that would lead to a very biased model as well. It would more probably just output very low values. And then we couldn't really populate this high ex situ stellar mass space, because then that would mean that we would have to run again the whole mocking procedure, and this is very computationally expensive. So we wanted to avoid that. So this is why we had to look for another ML architecture. So what we found was that if you use a self-supervised learning to extract more robust representations, you can actually go around this unbalancing issue. So in particular, we used the bootstrap your own latent technique, which what it does is using a pretext task as all self-supervised learning techniques, so that it can learn robust representations that do not really get affected of the augmentations that you add to your input image. So you have two different sets you have two models here, the online and the target model, that kind of mirror each other, and both are passed different augmentations of the input image, and then are mapping them to different representations and projections, and then the online model is trying to predict from the projection of the online model, the projection of the target model. So essentially, this means that it can get representations that are independent of the augmented features. And this, we actually found that, yes, this actually helped us overcome this unbalancing issue that we had. And now we actually could predict in the test set with high accuracy despite the added observational effects. So this actually meant that we were actually ready to go to this more exciting part, let's say, which is applying our model on real galaxies and actually infer something about their unobservable properties. So this is how this relation looks, what we got for around 10,000 galaxies from MaNGA. But then again, since this is application on real data, we also want to make sure that we are providing meaningful measurements of uncertainty. We don't have a ground truth here to compare. So of course, our model has to say, okay, I'm predicting this value, but with this kind of uncertainty. So to make sure that what we are outputting was also something that could be used as an uncertainty of the model, we did a statistical coverage test on the test set. And the goal here is to try to trace this perfect calibration line, which is the diagonal, and then it means that you have meaningful uncertainties. And you see that for our test set, we're doing quite well. Of course, for MaNGA, as I said, we cannot do the same kind of test because we don't have the ground truth, but it seems that the uncertainties there are also reasonable, a little bit higher, but this is expected. So this is what then you can do like more interesting things, like you can break down the total mass of these 10,000 real galaxies to in situ and ex situ stellar mass contribution. And you can see already from this kind of plot that for low or intermediate stellar mass galaxies, almost the entire total mass is coming from in situ star formation. And only for more massive galaxies, the ex situ stellar mass starts to become more important. So as I said at the beginning, we didn't have many samples, other samples to like cross-test our results, but we had some limited galaxies that this has been done before. As you can see, they all fall quite close to our relation, so this gives us a bit more confidence in our results as well. And then you can do other kinds of things, like trying to see if you can find other dependencies of ex situ stellar mass, for example, with morphology, star formation, even the host dark matter halo, and other things. But anyway, for the second part of the talk, I'm going to switch a little bit. So far, what we are trying to do is trying to see if with observables of galaxies, we can predict only one value for each galaxy. So can we do more than that? So for example, can we predict a 2D distribution of how this ex situ stellar mass looks in a projection in the sky? Which would be very nice to have, because then you would get even more information about the emerging history of these galaxies. Of course, this is a much harder task, so we have to go all the way back to the simulation space to see if this works. So like I first started this project like 2 years ago, I think. So back then it seemed like a very good idea to use a conditional variation autoencoder. It had a very well-behaved latent space and also could be used as a generative model. So the way we used it back then was trying to learn with the VAE, the low-dimensional representation of these unobservable 2D maps that we wanted our model to generate. And then we also made it conditional. So what the model was about to generate should be compatible with the observable features of the galaxy that we want to predict this 2D unobservable quantity for. And then during inference, of course, we moved to the encoder part. And then we had 2 different modes for inference. You could either sample directly from the learned prior, and then you use plug in your conditions as well to predict something compatible with these conditions. And also, like we also tried a more sophisticated approach of adding a normalizing flow so that you can learn the mapping of your complex latent space to a simple distribution, and then this would allow you to relax even further restrictions that you had on your prior, and then focus more on the reconstruction part. So we also did both of these inferences modes, and here I'm showing 3 results from 3 simulated galaxies from TNG 100. On the top, on the left, we have what we're trying to predict. So this is the ground truth of how this unobservable ex situ stellar mass distribution looks. On the bottom, we have these conditions. So these are the observable features that we plug in the network. On the right, I have the results of the model. So the first line is like just a reconstruction. So here I'm using also the encoder part, inputting the ground truth. So this is not something realistic, but this is just used as a baseline to see how well you can do. And then I have the 2 different modes of sampling that I said before. And as you can see, we get more or less relatively good results. The model seems to be able to regenerate more or less how this ground truth looks using all the conditions and the learned latent space. But then I'm going to plotting some summary results. These are per pixel level for my whole test set. Of course, you can see that the median of the residual in each pixel is lower for the reconstruction of the maps, which was expected. And what we found that was interesting is adding the extra complexity of the normalizing flow actually helped the model. As you can see, the median of the residuals when you sample with the flow is a little bit lower than when you sample randomly. But what we found when we did the coverage test again for the uncertainties is that it doesn't seem that the model is very reliable. As you can see, all the models are super overconfident in all three cases. So this is not something that you could actually use to go to real data. So when I came back to this project like a month ago, we started to discuss, okay, what we can actually use right now to move to the mock observational space more reliably. And since diffusion models are considered more or less now like the state of the art, we decided, okay, let's try that to see how it works. So very, very briefly, what diffusion models do is like they take your original image and then adding very gradually, step by step, some noise until you get to pure noise. And then during training, they try to reverse this process by removing again the noise gradually until you get back to your original image. So in our case, we wanted again to make this conditional because we want to do inference using the observable features for each galaxy. So again, the diffusion model, we want to be able to generate samples from this unobservable quantity of how the 2D ex situ stellar mass fraction looks. But then we wanted to make it compatible with our observables of each galaxy. So we also plug them in during sampling. So this is super preliminary results. I did this close like last week. So here on the left, this is from 3 galaxies from the train set. So here on the left, we have how the conditions looks for these galaxies. We are using 2 different sets of maps as conditions. And these are things that you can actually observe. So it's the stellar mass and the stellar velocity dispersion of the galaxy. And here I'm showing how the ground truth looks, 2 different samples, the median when I sample multiple times, measure of uncertainty, and the residuals. And you can see that we get almost 0 residuals. So this is quite promising, but also we are still in the train set, so that doesn't say much. When we go in the test set that the model has not seen before, you can see that the residuals go a little bit higher, but still the model is able more or less to reproduce how this ex situ stellar mass fraction looks. And again, I'm gonna point this out again, that we also always want to make sure with simulation-based inference that you marginalize over different cosmological simulations. So again, you have to go and do this out of distribution test. So for that, we had to go and forward model some Eagle galaxies because a mock data set from Eagle doesn't exist for manga. So this is a very expensive process, I said before. So I only did this for a couple, for some galaxies, not a couple, hundreds, some hundreds for the Eagle test set. As you can see, our residuals are much higher now. And of course, we're out of distribution, that's expected. But I was happy to see that at least the model is not completely unreasonable. So more or less, it manages to learn something that it's more generalizable. And then again, going to these summary statistics as before, you can see, okay, that of course the residual on the train set is much lower and the out of distribution was much higher, but the coverage test at least now looks a little bit more reliable. So I was thinking, okay, let's train this more and more. So we know that the more you train diffusion models, they learn even more finer details and they tend to work better. But what I found in my case, this wasn't really helping. So as you can see, for the train set, the residual is now practically 0, but it seems that the model is clearly overfitting. So the uncertainties are getting less and less reliable, even for the test set, but also for out of distribution. So yeah, this is something that I need to figure out how to solve before I can actually go and apply this on real data. But yeah, hopefully in the coming weeks. So the goal of this project is actually go and get this kind of maps for real galaxies again. So if we have this kind of 2D distributions from real galaxies, it would be very cool to see if we can find different patterns of groups of how this ex situ stellar mass is distributed in galaxies. If this is somehow connected with different galaxy properties, for example, if spiral galaxies tend to have more ex situ mass in certain regions or something like that, or even with cosmic environments that galaxies could be found. So I'm quite excited to see if this will work just to do this scientific analysis as well. And then like, oh, this video also doesn't play. Anyway, so looking ahead, like as a future project that I would really like to do is trying to see if you can push this even further. So now what we're trying is to predict this ex situ 2D map, but at the same snapshot as the galaxy currently is. but it would be cool to see if you can go back in time and actually like see how this evolved across redshifts. So you can again imagine that here on the left, you can see a video of how this ex-situ distribution looks over across time, and then you can actually see how mergers affect, like in a more visual way, this galaxy. And even further down the road, if you can predict full merger trees with only from observables, this would be also super interesting to have. So of course, to do all this, again, I'm going back to the beginning. There are many, many challenges that you need to take into account because you're applying this on real data where you don't have the ground truth to compare. You have to make sure that you're marginalizing over multiple simulations. Right now, all my results are only using two, so Illustris TNG and Eagle. But further down the road, you would really want to do this in a framework like CAMELS, where you have multiple cosmologies or astrophysical parameters. But of course, as I said here, you have this huge smoking bottleneck, which we really have to take care of. So like as a future, like a wish list, I would really love to have an accelerate way of how you can do very fast forward modeling, like making the smokes, I don't know, with some more advanced machine learning techniques or like rewriting the whole thing in something like JAX. And then you would really have this wealth of mock data that you could actually use to marginalize over multiple simulations and really calibrate your generative models to generate galaxy merger trees. And then you could go and apply this on different observable surveys, apart from MAGA, also like the incoming JWST data or other multimodal data. And like as a final remark, so if you had this kind of method, you could actually use this to create an equivalent of the multimodal universe that just came out today, I think, for mock data. So a lot of efforts in astronomy recently have tried to gather different modalities of astrophysical data in the same space, so you can recover them and use them probably to train foundation models. So if we had something equivalent for mock data, you could really use this for other kinds of problems, not just galaxy merger trees. Yeah, and maybe I am over time, so I'm just going to leave you with my conclusions. Okay. So, cool. So yeah, just for my conclusions, like SBI is a very powerful tool. It can really give us access to new knowledge, but we have to make sure that we are using it systematically. So in our case, that led us to give like the first observational constraints on the merging history of 10,000 galaxies from MAGA. Now we're trying to find some 2D constraints as well, but this is much harder to get. And yeah, like do it. It's good. Like it can give you an overview on galaxy evolution. Yeah, that's it.
Thank you. Anyway, questions for Eirini? So, can you go back to your slide where you said your problem was with this one, I believe, with more data.
Yeah.
Can you elaborate a little bit on what the issue is and what are your approaches to try to solve it?
Yeah, so what we found is like, the more you train, of course, the model starts to overfit the training data. So this is not usually with the case with diffusion models, but when you have a conditional diffusion model and your model is quite big, that it cannot eventually start to capture the whole training data set, this can happen. So here, the one issue I have, and I know that I have, is that I don't have a very big training data set. So before, for the 1D prediction, I had like 10,000 galaxies, but now I'm even more limited because I don't have, I have to cut at the ex-situ stellar mass fractions that I have, so that I have actually some information. So if it's just all in situ mass, then it's just a blank image. So I'm not going to use this kind of images. So now I have even less data. I have like 3,500 data. Which is not a lot to train a diffusion model. So one approach that I'm thinking to try to overcome this is trying to add some of augmentations or adding some noise in the conditions. So like if I complicate the conditions like by adding noise, maybe it will be harder for the model to overtrain. So yeah, I will try to work on that and see how this works out.
Thank you. Yeah, Phil.
So do you have a sense for how sensitive your inference is to the spatial correlations of the pixels in the MAGA images? Or like, for instance, if you randomize the pixels, do you still get an accurate inference out? Or does it learn like actual spatial pattern?
I'm not randomizing the pixels, so I think that the spatial correlations are quite important. So another approach I was thinking to this, like to overcome this overfitting, was trying to cut my images in batches so that I actually increase my data set. But then I think I would actually miss this important information in the spatial correlations. So I will try this and see if it actually makes it worse. But yeah, it's something to keep in mind. But maybe it's not so important. Maybe.
Yeah.
Yeah.
Thanks. Any other quick comments, questions, suggestions? Anything? David's here only today, I believe, but there might be a couple of spots maybe open still. Otherwise, feel free to join for dinner. Also, feel free to stick around and ask. Eirini is here today and tomorrow, and there's a schedule for her as well. If you do want to talk about any of the things she said today, please go ahead and sign yourself in. Let's thank both speakers. Thank you very much for very
Oh, really? Well, this is like, there's